So if you took all the actual pure lithium out of the smartphone that you might be holding right now, it would weigh less than a standard metal paperclip.
Right. It's tiny.
Yeah, but here's the thing. Without that tiny paperclip-sized amount of element number 3 from the periodic table, I mean, modern civilization as we know it basically just ceases to exist.
It really is entirely sobering to think about.
Yeah.
I mean, you remove that singular element from the global supply chain, and your phone screen just goes black tomorrow.
Oh, completely.
The laptop on your desk is bricked. Electric vehicles are just stranded on the highway. And even, massive sections of the power grid, which are increasingly relying on battery storage to stabilize wind and solar, they would just begin to buckle and fail.
Yeah, we are just utterly dependent on a material that honestly almost no one has ever seen in its pure form. And our mission for this deep dive is to trace the mechanics, the history, and the geopolitical chess match behind that dependency. We've gathered a really fascinating stack of sources for you today. We're pulling from scientific papers on atomic metallurgy, geopolitical reports that map out the global supply chains, and some fairly sobering environmental impact studies from South America.
Yeah, the environmental side it's heavy.
It really is. But we want to understand how this obscure metal became the undisputed backbone of the 21st century, the material that's basically referred to now as the new oil.
Calling it the new oil is honestly arguably an understatement, given our current technological trajectory.
Right, really? An understatement.
Oh, yeah. Nations are practically rewriting their foreign policies just to secure these supply chains. I mean, billions of dollars in global capital are being deployed to find it, extract it, and refine it.
Right.
It's this story of incredible scientific triumph, but, and we'll get into this, it comes with a highly resource-intensive shadow that is really challenging the entire premise of the clean energy revolution.
Yeah, and before we get into that massive geopolitical scramble, I want to unpack the sheer improbability of lithium's origin story. Because, we treat this metal like it was custom designed in some Silicon Valley lab specifically to power the digital age.
Right.
But this material was a completely forgotten scientific curiosity for, nearly 2 centuries. Okay, let's unpack this. How does something so ubiquitous today start as a complete unknown?
Well, what's fascinating here is that to understand that, we have to rewind the clock all the way back to the year 1817.
Okay, 1817.
Yeah. We are in the laboratory of a Swedish chemist named Johann August Arfwedson. And he's analyzing this piece of petalite ore, which is honestly a fairly unremarkable-looking mineral.
It's just a standard rock, basically.
Pretty much. And Arfwedson is meticulously breaking down the elemental composition of this rock, measuring the silica and the alumina.
But the math doesn't add up, right?
It doesn't. He accounts for all the known elements, and they only make up about 96% of the mineral's mass.
Oh, wow. So there's a chunk missing.
Exactly. There's this missing 4%. And that ghost mass turned out to be a completely unknown element. And because he found it locked inside a mineral, he named it lithium, which comes from the Greek word lithos, meaning stone.
Which is highly ironic. Here's where it gets really interesting, because lithium behaves absolutely nothing like a stone.
No, it doesn't at all.
Like when we hear the word metal, you instinctively picture something dense, right? Heavy, solid. I mean, if you drop a block of lead or iron into a bucket of water, it plunges to the bottom like an anchor.
Right, sinks instantly.
But if you take a pure piece of lithium and drop it into that exact same bucket, it literally floats on the surface.
Yeah, it is the lightest solid element in the known universe. I mean, it's roughly half as dense as water. Furthermore, it is so soft, you can literally easily slice through a solid block of it with a standard butter knife.
A butter knife. That's wild. And when Arfwedson discovered this soft floating metal in 1817, absolutely no one cared.
Not a single person.
There were no parades. Nobody predicted a technological revolution. For decades, it was basically just the ultimate indie band of the periodic table, playing in an empty dive bar, just waiting for the world to catch up.
That is a perfect way to put it.
I mean, it eventually found some niche applications, right? Like in ceramics, glass manufacturing, high-temperature lubricants for aerospace, even in medicine as a psychiatric treatment. But the digital revolution wasn't even a concept yet.
No, because the digital revolution required a completely different kind of power source. And the reason the digital revolution eventually chose lithium as its champion basically comes down to its atomic structure.
Right, element number 3.
Exactly. Lithium is element number 3. That means an atom of lithium has just 3 protons in its nucleus and 3 electrons orbiting it.
Okay, 3 protons, 3 electrons. Got it.
Right. And two of those electrons are tightly bound, really close to the nucleus. But the third electron, the valence electron, is orbiting further out.
It's loosely held, and the atom is, like, desperate to get rid of it.
Precisely. Lithium is highly unstable and highly reactive because it desperately wants to shed that third electron just to achieve atomic stability. And well, I mean, when you are trying to build a battery, an element that is incredibly lightweight and eager to shed an electron, that's the holy grail.
They're like the Olympic sprinters of the periodic table.
Exactly. Small, fast, packed with energy.
So let's break down how that actually functions inside the device you are listening to this on right now. I want to picture this mechanically because our sources get into the weeds here. Let's say my phone battery is a pair of hotels.
Okay, I like this. We can call them the anode inn and the cathode motel.
Love it. And the lithium ions, those are the guests.
Yes. And those guests, they travel between the two hotels using a lazy river, which represents the liquid electrolyte inside the battery.
Okay.
So when you plug your phone into the wall to charge it, the electrical current literally forces all those lithium guests out of the cathode motel, pushes them up the lazy river, and crams them into the anode inn.
And that process, just to use the scientific term from the sources, is called intercalation.
Right, intercalation.
Right.
The lithium ions physically wedge themselves into the microscopic layers of graphite inside the anode.
And because lithium ions are so energetic and unstable, they absolutely hate being packed into that graphite anode. I mean, they're under immense chemical pressure, just desperate to get back to the cathode motel.
Exactly. But there is a catch. When you unplug your phone and turn the screen on, you open the door for them to travel back down the lazy river to the cathode. But they are not allowed to bring their luggage.
And the luggage is that single outermost electron we talked about earlier.
You got it. Those electrons cannot swim in the liquid electrolyte.
So the electrons have to take the highway, and that highway is the external circuit. It routes out of the battery, travels through the phone's processor, powers the display, drives the speakers, and finally meets back up with the lithium ions at the cathode.
Yeah, and that flow of luggage, those electrons moving rapidly across the external highway, that is the electrical current. That is literally what powers the modern world.
Brilliant.
It really is.
Yeah.
And the genius of the lithium-ion battery, which, by the way, eventually won the Nobel Prize in chemistry for scientists like John Goodenough, Stanley Whittingham, and Akira Yoshino.
Oh, right. They won it in 2019, I think?
Yeah. The genius is that this process is entirely reversible. You can shuttle those ions back and forth thousands of times.
And because lithium is so incredibly light, we can pack millions of these little atomic sprinters into a very small space. I mean, that energy density is the entire reason the mobile world exists.
Completely.
You don't have to carry a 10-pound lead-acid battery in your backpack just to, check your email. It allowed technology to shrink.
It untethered us from the wall. But the technological evolution didn't stop at pocket-sized gadgets. I mean, once the proof of concept was established on a microscale, the engineering scaled up drastically.
Which brings us to the electric age. We aren't just trying to power a 6-inch screen for a day anymore. We're trying to store enormous amounts of energy to physically move a 2-ton machine down the highway at 70 miles an hour.
Right. Electric vehicles?
Yeah, and when you look at an electric vehicle, you aren't looking at one giant block of lithium. Our sources detail how an EV battery pack is actually made up of thousands of individual cylindrical lithium-ion cells all wired together.
Thousands of them. And they're managed by a really complex computer system to balance the charge across the whole pack.
And the scale goes even further than transportation.
Oh, way further. We are now relying on lithium for grid-scale energy storage because, the fundamental flaw with renewable energy is intermittency.
Right, the wind isn't always blowing.
Exactly. Solar panels only generate electricity when the sun is shining, and wind turbines only spin when the wind blows. If you want a stable power grid, you have to store that excess energy to use at night or on calm days.
So lithium is basically acting as the buffer for the entire electrical grid.
It is.
And looking forward, as we build, massive data centers to train artificial intelligence, and as robotics become more advanced, the demand for high-capacity, lightweight energy storage is just going to skyrocket even further.
Absolutely. If we look at the historical context, the 20th century, the industrial age, was entirely defined by oil.
Right.
Oil built modern cities, dictated foreign policy, fueled global economies.
Yeah.
As we move deeper into the 21st century, lithium is actively stepping into that exact same role.
So what does this all mean? If lithium is the new oil, Then whoever controls the lithium controls the future of transportation, technology, and energy security.
Precisely.
So where is all this material actually sitting?
Well, the global reserves are primarily split between two very different geological setups.
Hmm.
First, you have the Lithium Triangle in South America, which encompasses regions of Chile, Argentina, and Bolivia.
Okay.
These are massive, high-altitude salt flats. Second, you have countries like Australia, which mine lithium from hard rock mineral deposits, primarily a mineral called spodumene.
But our geopolitical sources make a really vital distinction here. Pulling the raw material out of the dirt or, the salt water, that's only half the battle. You have to process it.
If you do,
And currently, China completely dominates the global supply chain for refining lithium.
the statistics are honestly staggering.
Hmm.
China controls an estimated 60 to 70% of the world's lithium processing capacity.
Wow, 60 to 70%.
Yeah. It is a highly strategic bottleneck. You can dig up millions of tons of spodumene rock in Western Australia, but to chemically convert that rock into battery-grade lithium carbonate or lithium hydroxide,
Yeah.
it almost certainly has to be put on a cargo ship and sent to China.
And this processing monopoly has naturally triggered a frantic scramble in the US and Europe to build domestic supply chains, right?
Oh, big time.
We are seeing billions of dollars in government subsidies and private investments trying to stand up refining facilities outside of Asia just to ensure energy security.
It is modern-day gold rush. But, this global scramble brings us directly to the darker, highly complex reality of the electric age.
Wait, I want to jump in on this specifically because we constantly brand this transition as the clean energy revolution.
Right.
We celebrate moving away from fossil fuels, and driving silent zero-emission vehicles feels like a massive environmental win. But reading through the environmental impact reports we gathered for this deep dive, especially concerning the Atacama Desert in Chile, the contradiction is just glaring. Extracting lithium from those salt flats is not a delicate green process.
This raises an important question because you're absolutely right. It is an incredibly aggressive industrial operation. In the Lithium Triangle, the lithium is dissolved in underground reservoirs of salty water, or brine.
And to get to it, mining companies literally pump thousands of gallons of this brine to the surface every single minute.
Every minute.
They pump it into these massive, artificially constructed evaporation pools. I mean, if you look at satellite imagery of the Atacama, you see these vast grids of neon green and yellow geometric squares cut into the desert.
Yeah, the colors are unreal. And then they just wait. They let the desert sun evaporate the water over the course of 12 to 18 months, which leaves behind a concentrated lithium sludge.
But the desert is already one of the driest places on Earth. By pumping billions of gallons of brine out from under the surface, these operations are significantly dropping the local water tables.
Drastically.
Our sources detail how this directly threatens the local ecosystems, including populations of Andean flamingos, and it's devastating local indigenous communities who completely rely on the sparse water supply for agriculture and survival.
It really is.
It forces us to ask a very uncomfortable question. How clean is a revolution if the process of getting the necessary materials fundamentally degrades local environments?
It's the central paradox of our time. We are essentially trading atmospheric carbon pollution, the burning of oil and gas, for localized terrestrial and water degradation.
Right.
And by the way, the hard rock mining happening in places like Australia or even planned sites in the U.S., that isn't a silver bullet either. Spodumene mining requires massive open pits, heavy machinery running on diesel, and really extensive chemical processing to separate the lithium from the rock.
Yeah, we can't just ignore the devastating local impact to secure a global climate benefit.
We can't. And that tension is what's driving a massive push within the scientific community to innovate. I mean, the environmental and geopolitical limits of lithium are glaringly clear now. It raises the question of whether we are permanently locked into this specific element or if there's an escape hatch being developed in the labs right now.
So mechanically, what does the next generation of energy storage actually look like? Are we looking for the next new oil to replace the current new oil?
Well, science is aggressively pursuing alternatives.
Yeah.
And one of the most promising frontiers right now is the solid-state battery.
Okay, let's clarify that. Because solid state is a buzzword that gets thrown around a lot in tech articles. Mechanistically, how does it differ from the battery currently sitting in my phone?
Okay, remember the lazy river from our hotel analogy?
Yeah, the liquid electrolyte.
Exactly. In a traditional lithium-ion battery, that electrolyte is a liquid, and it happens to be highly flammable.
Right.
If the battery is punctured, or if it overheats, that liquid can ignite, which is why you occasionally hear those crazy stories about e-bikes or laptops catching fire.
Definitely seen those videos.
Yeah. So a solid-state battery replaces that flammable liquid with a solid material, usually a specialized ceramic or a polymer.
So the lithium ions are still moving back and forth, but they are moving through a solid matrix instead of swimming through a liquid.
Exactly. And the implications of that simple material swap are massive.
Yeah.
By removing the flammable liquid, the battery becomes exponentially safer. And because it is safer, you don't need as much heavy protective casing.
Oh, that makes sense.
Yeah, you can pack the lithium much more densely, theoretically doubling the energy capacity in the exact same physical footprint.
So an EV that currently gets 300 miles of range could suddenly get 600 miles without making the car any heavier.
That is the promise of solid state, yeah.
Oh.
But researchers are also looking beyond lithium entirely. A major area of focus right now is sodium-ion batteries.
Sodium, element number 11. It basically sits directly beneath lithium on the periodic table.
Right, so it shares many of the same chemical properties, which makes it a viable substitute for battery chemistry. But the crucial advantage is abundance.
It's everywhere.
Sodium is everywhere. We can literally extract it from the ocean. You don't need complex geopolitics or massive evaporation pools in the desert to find salt.
But there has to be a trade-off. I mean, if sodium is so abundant, why aren't we already using it?
The trade-off is weight and size.
Mm-hmm.
Sodium atoms are significantly larger and heavier than those tiny lithium sprinters.
Mm.
A sodium battery will never have the same energy density as a lithium battery. You wouldn't want to use one in a smartphone or a drone because the device would just be too heavy and bulky. But for grid-scale energy storage, where the battery is just sitting stationary in a field next to a solar farm, weight doesn't matter.
So we might see a divergence. Sodium handles the stationary power grid, which frees up the lightweight lithium exclusively for things that need to move, like cars and aerospace.
Exactly.
And if you add in the rapidly advancing science of battery recycling, where we treat old EV batteries as high-grade urban mines to extract the lithium back out, you really start to see a pathway to a more sustainable electric age.
Definitely. But for today, and for the foreseeable immediate future, lithium remains the undisputed king of the board.
It is the imperfect, incredible engine driving humanity's transition. It powers the device you are listening to right now, it stores the wind energy that keeps the lights on, and it will likely power the humanoid robots and AI networks of tomorrow. And it is doing all of that quietly, completely out of sight.
Truly a hidden force shaping the 21st century.
Which brings me to a final thought I want to leave you with today. The next time you unplug your phone from the wall, or, the next time you're standing at an intersection and watch an electric vehicle glide silently past you, I want you to take 1 second to appreciate the sheer, ridiculous improbability of the physics involved.
It's an unimaginably long journey from a Swedish laboratory in 1817 to a global superpower.
You are interacting with the legacy of a 200-year-old rock discovery. A bizarre, soft, floating metal that basically sat dormant and ignored for centuries, just waiting in the dark for humanity to invent a world complex enough to finally need it. That is the true magic of the periodic table. We don't invent these capabilities, we just slowly learn how to unlock what the universe has already built.
Hidden in plain sight, just waiting for the right moment.
If you want to dive deeper into the invisible building blocks that make up our universe, be sure to follow and subscribe to Atomic 118. We are going to be bringing you more incredible stories about every single element on the periodic table, exploring the science, the history, and the hidden mechanisms of the world around us. And if you enjoyed this deep dive, please share it with a fellow science enthusiast and leave us a review. It really helps the Atomic 118 community grow so we can keep bringing you these explorations. Until next time, keep looking closer.